4, 5-element partition. This time, we need to tighten the estimate using 5-element partition. The 3-element partition still a little short of what we want to have the result. So now we still using the same way, but this time our groups will have larger size, 5-element. All right. Now let's repeat that procedure. Yeah. All right. So here a list of properties from 3-element partition. Yeah. All right. Our goal, we want to get big theta of n, linear efficiency. But, 3-element partition, we just get big theta of n log n. We cannot take it. Okay, yeah. But we feel, based on our, intuition, we feel, so this method is pretty promising. Yeah. If we can make our estimate better, we can still use it to get a job done. Yeah. All right. So that's the reason we want to give it another try. Yeah. This time we use 5-element groups. All right, so let's look at the whole procedure another time with group size 5. All right, yeah. So each group 5 elements. All right, yeah. Still, we use the convenient size number for n, 5r, and r, odd number 2s plus 1, so n equals 10s plus 5. Yeah. As before, yeah. And find all the medians of these groups. Yeah. So here the question. So one question I want to ask, in order to find the median of 5-element array, how many comparisons do you need? In order to find the median of 5-element array, yeah, so here, let me write median of 5-element array. How many comparisons do you need? Yeah. Before I give you the answer, let's recall I did one example. So similar to this one example. At the end of the insertion sort. At the end of insertion sort, I did example sort a 5-element array. Still remember that example? In that example, the best we can do, 7 comparisons. Yeah, so we try very hard and we get 7 comparisons. To get a median, usually it should be faster than sort the array, right? Because we do not have to sort. So usually it is better than sort an array. Okay? Yeah. All right. To find the median of 5 elements, the answer is 6. 6 comparisons. Yeah. This is also a challenging question. Very challenging. So if we want to try, that's good. Yeah. Later, when I have time, I will explain how to solve this problem. Find the median of 5-element array. 6 comparisons. Yeah. The method also very smart. using the elimination method. Yeah, it's a very good example. All right, so here we just use the result directly. Each group, we just need 5 comparisons. Okay, each group 6 comparisons. For the worst case, 6 comparisons. We can get that. Yeah. All right, so now next step, find the median of the median, M star, median of all these group medians. All right. With that element, by recursive function call, with that median, then we can divide it, all the elements except M star in 3 different groups. The first group, those elements that are guaranteed to be less than M star. Okay, see, you can see this circle, guaranteed to be less than M star. Total number 3s plus 2. Set 2, part 2, set 2, these elements, those elements that are guaranteed to be greater than M star. All right. Then the remaining element, yeah, still 3s plus 2. Then the remaining elements, we don't know greater or less, but if we can do more comparisons, we can get that part. Yeah. These elements, we have 4s elements. All right, so here you can see we just repeat the 3-element partition, but using the 5-element group setting. Yeah. Same as similar to the previous example case. Yeah. All right, so now 5-element partition element. So we use the same diagram, but this time our numbers must be updated. Region 1, 3s plus 2. Region 2, 3s plus 2. Region 3, subregion A, little a numbers. After 4s comparisons, we can get that number. Region 3, part B, little b number of elements. After that same 4s comparisons, we get this number. Yeah, we know the range for little a, little b. Yeah, and also a plus b equals 4s. All right. Now we can derive recurrence inequality. Inequality. All right. Yeah. We use the function S solution, number of comparisons for size n problem. S of n less than or equal to the first term, finding all the group medians 6n over 5. Each group we use 6 comparisons. The number of groups approximately n over 5. Approximately. So it's okay. We know in our estimate, we frequently use this way. Yeah. Second term, 2n over 5. So what's that? 2n over 5. 4s, right? 4s. If you convert 4s to n, yeah, convert 4s to n, you get 2n over 5. Yeah, because n equals 10s plus 5. You can drop 5, n approximately equal to 10s, 4s, 2/5 of n. So that's the second term. The third term, median of median. The size is n over 5, s parenthesis n over 5. Yeah. The last term, after we drop smaller subarray, the remaining larger subarray, the largest possible size, 7n over 10. Because the smaller subarray approximately 3/10 of n. 3s, that's 3/10 of n. So drop that part, remaining 7/10 of n. Yeah. All right, that's the new recurrence relation. After a little simplification, we need to do our new estimate using this new recurrence relation. All right, then the last step, the final step, draw recursion tree to get the final estimate. Let's do the last step. All right, yeah, so it's pretty straightforward. So let's do it. Estimate by recursion tree. When we start, we put S of n at the root of the recursion tree. Then look at the inequality, the right-hand side. Non-recursion term, 8n over 5. And the two recursion terms, 2 branches. So we draw 2 branches. And collect non-recursion terms, 3n over 5 for the top level. Second level, so here the key, let's estimate the second level non-recursion part. Based on 3, so here, you may ask question, how do we get the non-recursion term each level? Oh, for each node, for example, that one. Look at this. 8n over 5, can we treat as 8/5 times the problem size, right? Yeah, here we understand this way. 8/5 multiply the problem size. That's the way we estimate non-recursion term. Here, let's do the estimate. 8/5 of the 8/5 of the problem size. What's the problem size? N over 5. So that's why it is 8n over 25. Yeah. Similarly, this side, we can do the same way. Yeah. So 8/5 multiply 7n over 10. Yeah. So that way. Then, if we add these two numbers together, we get 36n over 25. 36n over 25. Okay? Now you see the key difference. If we compare it with our 3-element recursion tree, you can see the key difference. The key difference is this number is smaller than the previous number. Yeah. Why smaller? Because we can write it as 9/10 times the previous number. Smaller, less than 1, 9/10, less than 1. So the second level non-recursion term is reduced by 10%. That's important. This key property gives us a hope, and we can converge faster. That we can make our the number of levels to get to the bottom faster than not that faster, because number of levels still log, right? Not that faster. But when we do the accumulation on the non-recursion terms, we can drop that log. That's the key. We have a chance to drop that log. How? You will see it. I will show you. We can drop the key. We want to drop that log factor. So see this less than 1 multiplier. Less than 1 multiplier gives us a hope to help us drop the log factor. All right. And Number of levels still log of n, but this time because divided by 5, log base 5. More specifically, log base 5. So this is our estimate for number of levels. All right. Then, because our goal, we want to drop this number. So here we say this number is not important. If we can drop it, this number is irrelevant. Yeah. Next, let me show you how do we drop that. All right. Then we accumulation step. This is accumulation step. When we do accumulations, the common factor 8n over 5, we factor it out of the parentheses. Inside the parentheses, each term, the power of 9/10, some power of 9/10, integer power of 9/10, right? Yeah, but here you can see the number of terms is not important. Why? Because this geometric series. So this is a geometric series. This geometric series converges pretty fast. If it is converges very fast, we don't worry about number of terms. Even infinite many terms, we can get it converge to certain number quickly. Converge to certain number. That's it. Yeah. All right. So here we have a formula to find the summation of the infinite geometric series. Yeah. So the formula is this. Yeah. Leading term 1, right? Leading term 1 over 1 minus the common factor. 9/10, that's the common factor. So 1 minus 9/10. Yeah. So after simplification, we get 16n. It's a constant. 16, a constant multiple of our problem size n. Then you can see our conclusion. We achieve our goal. S of n belongs to big theta of n. So you can see, same method. The only difference is changing from 3-element partition to 5-element partition. Yeah. All right, so now we complete. We solve the whole selection problem. Conclusion is we derived linear solution. So this is a linear solution. Okay? We drop that log n, linear solution, the conclusion. Yeah. So this solution is pretty complicated. So for this class, probably among the top. The complexity pretty much among the top. Yeah. Hope you can understand. Yeah. Try your best to understand the whole procedure, including the recursion tree part. All right, so let me stop the video C.4 and our whole part C of module 4. All right. Yeah.